Hi again, everybody, and welcome back. Well, if you hung with me through that last problem right there, that last example, example 9.5, well, you're in for a little bit of good news because this section on collisions is actually, I think it's, I personally think it's easy, but I think a lot of students find that collisions, especially inelastic collisions, are easy to comprehend. We'll get into elastic collisions later on, but let's just define what elastic and inelastic collisions are. Well, first of all, any collision is a place where two objects that have mass strike each other. All right, and they have some sort of force in between them that collides, and that force causes the masses to respond differently than the way they had originally been going. Okay. So we're going to assume that the force only exists between the two parts. So think of it as like, I don't know, two cars. All right, two cars moving towards each other. Okay, this going this way, and this car, a little differently shaped car right there, going that way, right there, and when they collide. And generally we want to try to avoid this, but when cars do collide, the forces that they experience, we're going to say that the forces that the cars experience are simply the force in between the two cars. You might say it's an internal force. All right, we're going to say that there's no real external forces acting on the cars, or at least not in the direction of their motion. All right, external forces meaning like, I don't know, force from the road or force from friction or air resistance or anything like that. We're really only counting on the forces that exist between the two cars right there. All right, that's one of our conditions right here. Two different kinds of collisions that we're going to talk about are elastic collisions. Now what that means is that all the energy of the system is conserved. Think of something that's elastic. A great thing that is elastic is one of those super balls. You know, there's maybe they're about an inch diameter, really kind of dense rubber balls that you get at the supermarket in those eggs. Right? You put the quarter in and you get those little super balls. They bounce really, really high because they conserve energy. All right? They are elastic. You slam them down on a concrete floor and they bounce up really, really high. All right? All that energy is conserved. Well, the first kind of collision that we're going to talk about, however, is not elastic, but it's what we call inelastic. And pretty much every single collision that takes place is in some part inelastic, because that means that some of the mechanical energy, that is mechanical energy, the kinetic energy or the potential energy, is somehow lost. All right, you might say, remember we talked about the non-conservative forces. Non-conservative forces cause the system to lose energy. Well, you can say the energy is lost in inelastic collisions right here. That certainly happens with cars. All right, cars have energy. This car has kinetic energy. This car has kinetic energy, and when they crash into each other, the cars kind of crumple up, and a lot of that energy is absorbed in the cars crumpling up, and so the final energy of the two-car system is a lot less than it was going into that collision right there. Which, by the way, is why you hear terrible sounds when cars crash into each other. In a lot of cases, they heat up because of all the forces. I don't know if sometimes I don't know if you see two cars crashing and they light up. That's another way that energy is lost. Well, if you see two cars crashing into each other and they're lighting up, you might want to start running. But in most cases, we experience some of that lost energy in the form of sound or in heat, okay? But it means that a lot of that energy going into the collision is somehow lost. And the whole system after the collision has less mechanical energy than it did. I'm sorry, I think I said it backwards. Coming out of the collision has less mechanical energy than it did going into the collision. Even those super balls, those that you get at the supermarket, in some way, they're actually inelastic. They're not perfectly elastic because you slam them down onto the ground and they bounce way up in the air. Okay, but even so, in that collision with the ground, a little tiny bit of energy is lost. They're novel, they're interesting to us because for the most part they do conserve energy, but even a little tiny bit of energy is lost due to friction and sound, right? I mean, you throw it on the ground, you hear a sound. So a little bit of energy is lost. So they're not perfectly elastic, but the types we're going to talk about is where energy is lost. The first type we're going to talk about is where energy is lost, and we call those inelastic collisions. So an inelastic collision, what is true is the fact that the momentum of the system is conserved. All right, now I want you to add something right here. The net momentum of the initial momentum of the system and the net final momentum of the system is going to be the same. Momentum is always conserved. But what is not conserved, like we said before, is energy, especially kinetic energy. Like I said before, two cars may have two very high kinetic energies right here. All right, it doesn't matter what direction they're going, they both have kinetic energy, and so the kinetic energy of the system is very, very high. When they crash into each other and crumple up, both of those cars stop. All right, so the final kinetic energy is very, very different from the initial kinetic energy going into that collision. Now, sometimes when cars collide, they crumple up and then they bounce off of each other a little bit. But for simplicity's sake, when we are going to start looking at our inelastic collisions, we're going to look at what we call completely inelastic collisions. All right, entirely inelastic, and that means that the energy is so lost in the system that the two objects that crash into each other stick together. All right, they become like one unit and they don't come back apart. And that actually happens sometimes with cars, right? Cars hit each other hard enough that the metal crumples around one another and the cars kind of stick together and they become like one twisted, mangled mess. All right? So we call this completely or perfectly inelastic. And that's going to be the theme or the topic of the very first example that we're going to do. That's going to be example 9.6. And a great everyday example of that is the example of football players. All right, so we're going to do this example right here. And that'll be it for this video segment, all right? But this is a great example of a completely inelastic collision. All right, so a running back, so he's the guy in red, all right? He's got the football. A 95-kilogram running back. Let me just write that over here. Mass. I'm going to do mass of RB, okay, because there's going to be another football player with a different mass, as 95.0 kilograms. All right, runs towards the end zone. That's that white line right there. At let's say 3.75 meters per second. Sorry, I'm so ambiguous about that, but I have to shrink it down. Yeah, there we go. Sorry, I had a menu bar right in the way and I couldn't read that. 3.75 meters per second. So the initial velocity, VI of our running back, is 3.75 meters per second. And by the way, see this axis in the bottom right here? We're calling that direction positive x. All right, positive x. Oh, you know what? 3.75 is written here already too. Okay. This is interesting. This is denoted with a in unit vector notation, x hat. I think we all agree that the football players aren't like flying up into the air vertically, so they're all kind of moving in the x direction. So I'm not gonna do the x hat on the end. I think we all agree that this is all happening on the x-axis. We also have a linebacker. He's the guy in blue. All right, he looks kind of like a Downingtown player right there. The mass of the LB for linebacker is, and they tend to be a little bit bigger than running backs, 111 kilograms right there. And his initial velocity of the linebacker is in the opposite direction of that of the running back, right? That's going to be negative 4.10 meters per second. All right? I don't know why parentheses around that. Oh, because of the negative. Okay. All right? So, each of these guys has a momentum. Mass times velocity here, mass times velocity here. But we're going to find that when these guys collide, the linebacker being a good linebacker and being a good tackler, what he does and what you should do if you're playing football is you should wrap up the other guy. You need to wrap your arms around him so that these two players become one mass. And this guy is hoping that they stop before the goal line. This guy is hoping that they stop after the goal line. All right? We don't care about that, but we do want to find out what their velocity is after the collision. All right? Their final velocity after the collision. So I'm going to write that in, I don't know. I'll do it in purple because that's what red and blue make. All right? So final velocity of the system is what we want to find. So that's part A right there. And part B is asking, not V, K initial of the system and K final of the system. Both of those we want to find out, okay? Now, I didn't leave a whole lot of space to write, so I'm going to have to shrink this down a little bit. Hopefully you can still see it okay. All right, let's solve for part A. Part A, we want to find the final velocity of the system. All right, well, what do we know to be true? We know that the net momentum of the system initial is going to be the net momentum of the system final. Okay? Well, what is the net initial momentum of the system? It's going to be the combined momenta of this guy and this guy right here. So let's just do them one at a time. I'll color code them back in red and blue so that you can see which one is which. So the mass of the running back times the initial velocity of the running back plus the momentum of the other guy, right? The linebacker, plus the momentum of the linebacker. So that is the mass of the linebacker times the initial velocity of the linebacker right there. That is the initial momentum of the whole system. Now remember, we're trying to solve for the final velocity of the system right here. Okay, but let's write a statement about the final velocity. Let's write a statement about the momentum of the system finally. And I think we'll see what we're solving for is going to be in that. Well, what is the final momentum of the system, or how would we state that? Well, finally, after the collision, that system is one mass. All right, so the mass of the system right here, I am going to write it in purple. It's going to be mass of the running back plus the mass of the linebacker, right? Because they're wrapped up. The linebacker wrapped his arms around the running back, and so they're one giant mass. So there's going to be one big mass right here, and that mass is going to have a final velocity of that running back linebacker system. We're just going to call it sys, okay? Because they're one big system right there. This is what we're solving for. All right, so I think it's pretty obvious what we need to do to solve for it. We just need to divide by this whole part right here. All right, and divide it, and it'll come down underneath here. Then we're going to plug in our values and get our final answers. All right, I'm actually going to use purple from here on out. So we're going to take this side and divide it by mass of both right here. So mass of, in fact, you know what, to save space, here's what I'll do. I'm going to just kind of cancel that and put that below right here. Mass of the running back plus mass of the linebacker right there. And now down below, I'll have to shrink this down yet even more. I think I'll have space now. Now down below, I'll actually write in our values and we'll plug it in. All right? But dividing this down, we now have our equation solving for the final velocity of the system, which is what part A is asking us for. Okay? So let's plug our values in. Mass of the running back is 95 times what was his initial velocity? That was 3.75 meters per second. All right? Plus mass of the linebacker, 111, right? 111 kilograms times that negative, and this is why the velocity direction is important, negative 4.10 meters per second that he was originally going at. And all this is going to be divided by the mass of both. So 95 plus 111. That's going to give us our final velocity of the system. I'm going to grab my calculator. I'm going to key that in, and I imagine you will too. Okay, and I get that the final velocity of the system is negative 0.48 meters per second. That's our final answer for the final velocity of the system. So, who wins? Who wins the tackle? Does the running back plow through the linebacker, or does the linebacker stop him? It looks like the linebacker wins because ultimately that whole system is going in the negative direction. So the linebacker appears to be pushing the running back, which is good because it looks like the linebacker is a Downingtown player, and we're all happy. Okay, so there's our final velocity of the system. We set the initial momentum of the system, that is the combination of the two momenta of the two things that are moving, equal to the final momentum of the system, and then solve for our final velocity. Let's solve for the initial and final kinetic energies of the system, and then we'll be done. Okay, so for part B, what is the initial energy of the system? Well, each of these guys has energy. He's got mass and velocity, and since kinetic energy it is not direction dependent, the total energy of the system is going to be this guy's energy in this direction plus this guy's, I shouldn't say a direction, this guy's energy running that way and this guy's energy running that way. We're just going to add them up. All right? So kinetic energy initial is going to be kinetic energy of the running back. Oops, I'm putting my my letters backwards. RB plus kinetic initial of the linebacker. All right, let's key them in and see what we get. Initial of the running back. Well, kinetic energy we know to be 1/2 mass of the running back, so that's 95 times what was his initial velocity? 3.75 meters per second, and that's going to be squared, right? Because after all, kinetic energy of anything is 1/2 mv squared. So that's our running back, and our linebacker is 1/2 times 111 times 4.10 squared. All right. Now, I didn't put the minus sign in there because, well, it goes away anyway, right? It anything negative squared is going to be just a positive value. So I left the minus sign out, but if you really want to, you can put the minus sign in there. It'll go away. All right, let's add those up and see what we get for the total momentum of the system beforehand. Okay, I got that the running back had about 667 joules of kinetic energy, and the linebacker had about 930 some, I want to say. So totally, that added up to about 1,600 joules. Kinetic initial of the system is 1,600 joules of kinetic energy. All right, let's compare that to the final energy of the system. Now, we're not going to have to write quite as much because finally, after the collision, it's all one mass. It's all one system. So for kinetic final, we only have one kinetic to calculate. That's going to be 1/2 times mass of the system times final velocity of the system, which we just calculated. Okay, which we found in part A. So that's 1/2. What's the mass of the system? Well, that's 95 plus 111, right? I get 206. That's 206 kilograms of those two guys together. Times what's the final velocity of the system? It's this guy right here, 0.48 meters per second. Not moving very fast because they slammed into each other. They lost a lot of energy, and they're just kind of moving in the backwards direction. So that's 0.48 meters per second, and that value is, of course, squared. All right. So what do we get if we get 1/2 times 206 times 0.48 squared? I get 23.7. 23.7 joules of kinetic energy final of the system right there. Not a whole lot. The initial kinetic energy of the system was 1600. These guys were running at each other, massive guys running at each other with full speed. There's a lot of energy going into the system. Going out of it, not much energy at all. Assuming I did my math right, I think I did. Okay. Well, where did a lot of that energy go in this inelastic collision? If you've ever watched big, heavy hits on football games on TV, you can hear it in many cases. Now they've got microphones all over the field, but it doesn't take much to be able to hear a lot of these hits. A lot of the energy is dissipated in the form of sound. All right. So when these guys crash into each other, all right, you hear a lot of sound coming off of their pads. Energy is also absorbed into the pads, which, by the way, is why they wear them, right? So your brain doesn't, or your bones, your muscles don't absorb all the energy. Of course, there's debates as to if that's good for your brain at all, whether you're wearing a helmet or not. But a lot of energy is dissipated into the players right here. All right, you hear a sound. The pads crunch. Sometimes you see pieces of helmet flake off and chip up and go into the air. So a lot of that energy is lost in this big collision right here. So this is a good example of an inelastic collision, a perfectly inelastic collision, where the momentum is conserved, but the kinetic energy clearly is not. All right. Thank you for following along with me. That one was also much kind of a longer video, but if you have any questions, make sure you come see me, and I'll be glad to help you out. Thanks for following along. I'll see you on the next one.